Good afternoon, everyone. My name is Peng from Tsinghua University in China. Today I'm going to be talking about low-cost and high-performance microchannel integrated biosensor systems. First of all, I want to talk about label-free biosensor, and then talk about microfluidic channel. And we try to integrate the microchannel with the biosensor and use this system to detect tool markers. The last part is conclusion. Since I'm the first speaker in this session, so I'm going to take some time to give you a brief introduction of the label-free biosensor and the tool marker to save other speakers' time. The tool markers are small biological molecules exist in blood or tissue. The high level of concentrations of tool markers usually indicate certain cancers are very likely present in human body. So that's why we need to know their concentration. The conventional way to detect the tool markers includes the ELISA or magnetic beams and so on. They are very accurate and their detection limit can be very low. However, they need time-consuming labeling process and they need sophisticated optical detection system, and they are not low cost and they cannot be portable so far. On the other hand, the label-free biosensor doesn't need target labeling process or sophisticated optical detection systems. They are very low cost, the operation is very easy, and they can be portable. For the label-free biosensor, we immobilize the antibodies on the surface of sensing material. Each type of antibodies can only absorb certain types of antigens, or tool markers in our case. Their relationship is just like the lock and the key. So after the absorption of those tool marker molecules, the physical properties of the sensing material, including its carrier density and the carrier mobility, will change, resulting in different resistance values of our sensor. So from the resistance shift, we are able to know the concentration of tool markers. The sensing material used here is carbon nanotube, or CNT. It's one-dimensional carbon materials, which is very sensitive to the absorption of ions or small molecules because all its atoms on its surface. Layer by layer self-assembly process was used in our experiment. Here's how we did it. First, we immersed the substrate in PDDA solution, which is positively charged, and then immersed the substrate in the PSS solution, which is negatively charged, and then put it back into PDDA, and then into CNT solution, and then back to PDDA and CNT several times. So the layer by layer CNT film can be grown on both sides of the substrate in this way. So you can imagine. We just keep one side and pattern to desired shape by using photolithography and oxygen plasma dry etching. The picture on the right top shows this sandwich structure of our layer by layer CNT film, and the FCM image on the right bottom clearly shows it has the porous structure of this film. With this porous structure, our CNT film can absorb ions or molecules more efficiently in this way. The regular methods to use the label-free biosensor is just like this, or like this. We have to immerse almost the entire chip into the antigen solutions, which is gonna waste a lot of antigen solution, which is very precious. Besides, since we need to put almost the entire chip in the solution, the chip will be contaminated after the first measurement. We cannot use one chip to detect multiple targets in this way. So to solve these problems, we come up with the idea and integrate the microchannel with the layer by layer CNT label-free biosensor. With the microchannel, our sensor consumes much less solution, and we can use one chip to detect multiple targets in this way. The microchannel we use is based on titanium oxide nanoparticles, which can be derived from the following chemical reaction. The titanium oxide nanoparticles, you can see from this SEM image, is about 150 to 200 nanometers in diameter. And the water contact angle on titanium oxide coated surface, according to our experiment, is almost 0 degree, indicating it's super hydrophilic. On the other hand, the water contact angle on silicon oxide surface is about 50 degrees, so it's relatively hydrophobic. Therefore, if we have a titanium oxide microchannel on the surface of silicon oxide, the water of the solution will be restricted in this titanium oxide region and flow along the channel. If it's so, we test it. The channel on the right in this picture is about 3 millimeters long and 100 microns wide. Its depth is about 500 nanometers. And the very beginning, we'll put the droplet water in the reservoir, which is not shown in the picture. It's connected to here, this end of the microchannel. After about 0.8 seconds, the water flows to middle. The darker color is the water. I don't know if you guys can see this clearly. After about 1.5 seconds, the water flows to the other end of the microchannel. This experiment proves that the water of the solution can be well restricted in the microchannel, and it can flow along the channel rapidly, less than 2 seconds. So we try to integrate the microchannel with our label-free biosensors. This is how we did it. First, metal lift-off process was used to fabricate the electrodes of the biosensors. And then we use HF wet etching to etch the silicon oxide layer to form the microchannel, and then use SF6 plasma to etch the silicon substrate beneath silicon oxide to make the trench even deeper. And then we immerse this sample into the solution and to coat the sidewall and the bottom with the titanium oxide nanoparticles to make the channel hydrophilic. Droplets of water of solutions in the reservoir can flow onto the layer-by-layer CNT sensor automatically through this microchannel. This is the SEM image. It shows the details of our sensor. So we can see the layer-by-layer CNT films here, and 2 electrodes, and the microchannel in the center. With this method, we are able to fabricate not only 1, but 3 or even more sensors on one chip, and each one of them connected to a microchannel, the black ones in this picture. So different types of tool markers can be detected on one chip simultaneously in this way. We use this system to detect lung cancer tool markers since it has the highest death rate lung cancer in China so far. And according to the papers published, 3 important lung cancer tool markers are EN01, AXA2, and VEGF. They were introduced onto our layer-by-layer CNT film through the microchannel. And then we measure the CNT film's resistance shift according to the different concentration of those tool markers. And this picture shows the resistance shift of our CNT film versus time. We can see that after exposure to the EN01 antigen, the CNT film's resistance has a sudden shift and took about hundreds of seconds for our sensor to stabilize. And this measurement consumes about 10 microliter antigen solutions. And from this picture demonstrates that when the concentration of EN01 antigen increases, the resistance shift value also increases, and from 1 femtogram per milliliter to 100 nanogram per milliliter in this large range, our sensor has good linear response. And according to the definition of detection limit, the sense signal of the sensor should be larger than 3 times the standard deviation of the noise of the sensor, which is 0.02 in our case. So we can see that when the concentration of the EN01 is 1 femtogram, its signal is larger than 0.06. So that means our sensor can be used to detect the concentration as low as 1 femtogram per milliliter. The specificity is very important for the biosensor to recognize different tool markers correctly. And good specificity can reduce the chance of misleading during diagnostic. So we immobilize our sensor with different types of antibodies and use it to detect the different types of antigens. Let's see the picture on the left. The sensor immobilized with ANXA2 antibodies only very sensitive to the ANXA2 antigen. And this picture on the right shows that the sensors immobilized with VEGF antibodies are very sensitive to the VEGF antigen. So that means our sensor has a relatively good specificity. It doesn't have too much response to other kind of antigens. And this picture shows another measurement, the same meanings. The conclusion. We present a low-cost and high-performance layer-by-layer self-assembly carbon nanotube biosensor with a microchannel system integrated. And our sensor is able to give stable and precise results by consuming only 10 microliter solution. And our sensor has very good specificity. We acknowledge the systems of fabrication and characterization from Minnesota Nano Center and the characterization facility at the University of Minnesota. And thanks for your attention.